Compiled and interpreted approach to execution of programming language is an ongoing discussion. Using both compiled and interpreted approach at the same time is possible and is beneficial. This can be achieved by applying a just-in-time compiler to the bytecode instructions and then using the AOT compiler to cache the results and thus accelerate the virtual machine startup time. In this research, an AOT compiler is defined as the infrastructure that makes the decision on what code and data to store, how the code and data should be persisted, and when to load the code to make it reusable. Answering those questions is equivalent to exploring several known software engineering problems. The performance versus memory footprint trade-off, portability, and sharing possibilities are currently in the scope of this research. The project is focused on designing an AOT compiler as it was defined above for the Eclipse OMR framework. Eclipse OpenJ9 was the project inspiring early development of the Eclipse OMR AOT compiler. Our goal is to provide meaningful tools for AOT compiler constructions in Eclipse OMR for an arbitrary language runtime.
Runtimes that leverage Eclipse OMR technology often use the JIT API to initiate and control compilation. With this API, language runtime designers can define the OMR trees and compile them to machine code. However, ahead-of-time compilation requires that some of the addresses in the generated machine are changed to reflect the state of the current runtime instance. To address this problem, we implemented the relocation infrastructure in Eclipse OMR. Now, runtime designers can define relocations necessary for their particular language and use AOT compiled code in new ways. For example, we created an AOT compiler for WebAssembly that uses the relocation infrastructure to achieve, to achieve substantially faster execution of WebAssembly modules compared to JIT compiler on the load runs.
One of the research questions we are interested to explore is the storage options. The project has tackled one existing option and is exploring an alternative approach, each having their own pros and cons. We have adapted the shared class cache to create an extensible and flexible persistent cache format for Eclipse OMR. As with the relocations infrastructure, runtime designers can use the shared cache boilerplate code to implement a persistent code cache that suits their need. Our research aims to provide the portability versus performance trade-off by using different storage options. An alternative to shared cache for this research is the executable and linkable format ELF. ELF files are quite popular and in the same time are flexible and extensible by design, which makes them enhancing their use in Eclipse OMR an interesting research topic to explore. It also offers cross-platform support, which makes it also a portable option for storing AOT code and data. Based on the existing ELF generator module in the Eclipse OMR, we have designed and developed a shared object generator that stores all the AOT code and data in arbitrary sections. As this shared object is dynamic in nature, we can load AOT code and data using the DLOpen API at runtime.
The future developer the future developments in our research are aimed towards further exploring the identified goals. The approach we chose to explore is to design an AOT feature for Eclipse OMR based runtime environment and committing an abstract version to the Eclipse OMR codebase. Compilation control and improving the quality of the compiled code by allowing for tiered compilation are possible ways for extending this research. Improving OMR AOT support for a runtime environment targeting embedded devices is also under consideration. Thank you for your attention. We'd like to acknowledge the help of people on the project as well as people who work in Runtime's lab and helped us a lot with learning, process, code review, and suggestions.